Hello, everybody. Welcome to Markov Processes. My name is Jem. I will be your guide this semester. I'm pretty darn excited to be in this position because I love Markov processes. This is central to everything I do in my area of research. So I'm thinking and breathing and living Markov processes every day. And what fun to get to talk about it with you. This course is aimed at upper division undergrads or first or second year graduate students in math or statistics, or I typically get people from all over the place because Markov processes have applications all over the place. So I do try to keep it as self-contained as possible. Now, that said, this is a course in probability and shouldn't be your first. So if you know about things like probability density functions, probability mass functions, expectation, variance, if you've heard of distributions such as the exponential distribution or the binomial distribution, then you're in fine shape to take this course. I know some of you followed me over from mathematical statistics. Mathematical statistics is not a prereq here, but if you made it through that, I know you have enough probability to be fine here as well. So you're in good shape. If these terms seem unfamiliar to you, like expectation or the binomial distribution, I'd highly recommend going and taking a basic probability course first. If they're somewhere back there and you haven't thought about them for a while, you'll be okay. It'll come back to you. So let's get right into it. A Markov process is a stochastic process with something known as the Markov property. So there's a lot of words to unpack here. First of all, the word stochastic. The word stochastic essentially means random. And the word process, a process refers to something that evolves over time. Now, when you put these together, a stochastic process is a time-indexed collection of random variables. As an example, you might have random variables capital X1, X2, X3, etc. In this course, we're going to adhere to the convention that all random variables are capital letters for sure. Now, time here appears to be just discrete time, time 1, time 2, time 3, and I'm often going to want an initial time or like a start to this sequence, so I might have a capital X sub 0 up front as well. Time looks discrete in this example, but the random variables may be discrete or continuous, and we'll see eventually that time could be discrete or continuous as well. So there are 4 regimes to consider here: discrete time with discrete random variables, discrete time with continuous random variables, continuous time with discrete random variables, and continuous time with continuous random variables. In this class, we're going to talk about the first 3 of these regimes. I'm going to leave continuous time and continuous random variables for a later course in stochastic differential equations, because that's really what you need to think about that properly. So let's see, we've got to talk about what this Markov property is, but first, let's talk a little bit more about the stochastic process alone and settle on discrete time and discrete random variables. And we're going to stay here for at least a third of this semester. So suppose I have a sequence of random variables, capital X0. Now you see my initial value there. You might be starting from 1, then capital X1, capital X2, etc. The entire collection or process is denoted by putting like an X sub n in brackets like this, and then saying n goes from 0 or 1 to infinity. And often when I get lazy or you get lazy taking notes, we leave off the subscript and superscript. But if you see X sub n in brackets, it refers to the entire collection of random variables, the entire stochastic process. Whereas if you see just X sub n hanging out on its own, this is a single random variable. It is the value of the process at time n. Now, a Markov process is a stochastic process with something known as the Markov property. To define the Markov property, we need to know a lot about conditional probability. So you might argue, I might argue that conditional probability is part of the prerequisites for this course as well. It should have been in your basic probability course, but because it's so central to everything we're going to be doing in here at almost every moment, I do want to take some time right now to review conditional probability. And at the end, I'll come back and finally define the Markov property, and then we will have a definition for a Markov process. So let's talk about conditional probability. Suppose I have a standard deck of American playing cards. There's 52 cards, and I completely shuffle them so that I can completely randomly select a card out of the 52 cards. And now I'm going to ask you, what is the probability that when I do this, the card I select is a king? So if you know your standard American playing card 52 card deck, you know that there are 4 kings in those 52 cards. And if everything is completely randomly shuffled and randomly selected, as I said it was, then the probability you get a king is 4 out of 52 or 1 out of 13. But I want to mix this up a little bit. I'm going to randomly select this card and I'm going to look at it. I'm not going to show you. And I'm going to give you a hint about what's in my hand. I'm going to tell you that this card is a face card. So that means it has a face on it. That means it's a jack. There are 4 jacks, or a queen. There are 4 queens, or a king, and there are 4 kings. So now if I ask you, what is the probability that it's a king, given that you have this information, given that you know that it's a face card? Now it's like the universe has shrunk, the universe of possibilities. You now know it's one of these 12 face cards, and 4 out of 12, 4 of those are kings. So the probability it's a king is 4 out of 12, or 1/3. This is conditional probability, and we usually write this like this. So notation, what is the probability we get a king? And then a vertical line, which can be read as given, and then it's a face card. This is going to be 1/3. This is conditional probability. I have an awful lot of words in here. You'll usually see something like this using event notation from probability. Events are usually denoted by capital Roman letters like capital A, capital B, capital C, and these are not random variables, but they're sets. And it's usually convention as well to denote sets with capital letters. So if I let A be the event that I get a king, and B be the event that I got a face card, then what we were talking about in more compact notation is the probability of A given B, and that is in this example 1/3. When you take a basic course in probability, you surely look at some Venn diagrams, and I think Venn diagrams are amazing tools for remembering or coming up with rules for probability. So I'm going to let this omega, this capital omega, denote a sample space, which is going to be the set of all outcomes of an experiment, usually involving randomness, like drawing the card. And so the omega there could be, enumerating all 52 cards. So one element in omega could be a king of spades or something like that. And I am going to draw a Venn diagram consisting of a rectangle, which is just a graphical representation of omega. I know it doesn't look like it for this discrete example, but it's just, here's all your outcomes. Whether or not there's a space and a continuum is completely irrelevant. The rectangle just represents omega, no matter what kind of space omega is. And inside, I'm going to put some events or sets as circles. Now, unless you're given specific information that your events are disjoint and separate, or that one is completely contained in the other, when drawing a Venn diagram, I like to put circles in and give them a chance to have a little overlap, like this. Now, I want you to think of the area of any set or event here as representing the probability of that set or event, that thing happening. So I want you to think of the total area of this rectangle as being 1, and then the area of this circle that's labeled A as the probability that the event A happens. Once you do this, you can come up with so many different rules for probabilities involving these events A and B. You might be aware of the probability of the union of 2 events A and B. If you envision the union of A and B in this Venn diagram, that's going to be this entire shaded area. I've got different colors here. So I have A, one color, B, another color, and then the overlap sort of turned into its own color. But the entire colored in part here represents the set A union B. And if you want to find the probability that A union B, that new event, occurs, that is the area of this total shaded region. And one way to compute or to get this area is to take the total area of the A circle. So that's like the probability, we're thinking of probability as area, the probability that A occurs, and then add the total area or probability that B occurs from the B circle. And then note that you've taken the center twice. So you want to back that out and subtract the area of the intersection. And area for us in this way of thinking about it is probability. So we're going to subtract the probability that A intersect B occurs. This is a pretty standard formula that you learn about early on in a course in probability. But did you know I'm sure you did. Who am I kidding? There are many ways to write a probability for an event like A union B. And if you think of it in terms of area, then you can really easily come up with your own formulas by piecing together area in different ways. For example, I could get the probability of A union B, or total area, by taking the probability of A, or total area for A, and then adding the rest of B that's not in A. So like this sort of crescent moon kind of thing. And this set that's depicted like this is the set B intersected with A complement. So we now have a new formula for the probability that the event A union B occurs. We can write it as the probability that A occurs plus the probability of the event B intersected with A complement. This is probably not on your list or your cheat sheet for a probability exam. It's not a standard formula you usually know, whereas this one is. But look how easy it was for us to come up with this. So no more memorizing formulas. Just derive them as you need them by drawing the pictures. I mean, this isn't going to work in every situation. Like it's hard to express independence of events with a Venn diagram, but this is going to get you a whole lot of useful results in this course. And I think other places where you're doing probability. Venn diagrams, probability as area, and I now have two expressions for the same thing, which actually leads me to something I need to say before going on. So which formula do you use when solving a problem? Simply put, you use the one that uses the information that you are given, that you have. Now, if we're talking about just an actual homework problem in a course like this, and I give you probabilities for certain individual pieces, and I don't give you every probability. For example, I don't give you the probability that A intersect B occurs. You use what you have and what you can work with, and that's how you decide how to sort of chunk up this picture. It shouldn't be a scary thing that you can write down 10 different formulas for the probability of A union B. It should be a comforting thing that you can create that probability out of area in many different ways. So you should use the pieces of information that you have available to you. So now let's talk about conditional probability. I already wrote down the probability of A given B. Given that you know that B happened, what is the probability that A happened? But we talked about it in a very conversational way. So I'd like to come up with an actual formula for that using Venn diagrams. So here I have my whole universe, which is omega, the set of all possible outcomes for my experiment. And I have two events, A and B, depicted as circles in here. And I want to go for the probability that A occurs given that B occurs. And given that B occurs, you already know that your outcome is in B and kind of nowhere else in this rectangle. So what you're doing essentially is shrinking the universe. You're shrinking the sample space, which is exactly what we did in the card example with the king. We are shrinking all the possibilities that we're looking at down to, in this case, just the set B. And once you have that, once your entire omega is now really the set B, then you want to look at the probability that A occurs within this region, which is this shaded area right here. So the probability of A given B is this intersection probability, the probability of A intersect B, as a proportion of the total area left in this shrunken conditional universe. So as a fraction of, compared to the area for B. So over the probability that B occurs. This is the formal definition for this conditional probability. To go back to our card example, if we randomly select a card from a deck of 52 cards that have been well shuffled, and you want to compute the probability, you get a king, given that you know it's a face card. With our new formulation here, this is the probability we get a king and a face card over the probability we get a face card. And this is not exactly how I think you looked at it before. You just said, I'm going to shrink the universe and then sort of count possible outcomes in there. But we're going to get the same thing. So this numerator, the probability you get a king and a face card, that's just the probability you get a king, because if you get a king, you know you have a face card. So I can rewrite this as the probability I get a king when I randomly select a card from a deck of 52 cards. And that probability is 4 out of 52 because there's 4 kings in there. And for the denominator, the probability you get a face card, there's 12 in there. So when I randomly select a card from the deck of 52 cards, the probability it's a face card is 12 over 52. And when you cancel here, you get 4/12 or 1/3, which is fortunately the same thing we got before. We just sort of looked at things a little bit differently here. So now I'd like to talk about, this is my term. I don't think you'll see it out there in textbooks or online, but I like to talk about unraveling conditional probability. Because we have a conditional probability defined to be the probability of an intersection over the probability of the event after the conditional line. And you could use this relationship here to come up with a new expression that for the probability of the intersection. If I move this probability of B over to the left-hand side, we have that the probability that A intersect B occurs can be written as the probability that A given B occurs times the probability that B occurs. So this is my unraveling the definition of conditional probability as a way to write down a probability of an intersection in terms of a conditional probability. Now we can talk about the probability of B given A, and that would be the probability of B intersected with A over the probability of A. And of course, B intersected with A is the same thing as A intersected with B. You're probably kind of annoyed that I'm rewriting this, but I did. This is the probability of A intersect B over the probability of A. And so if you take this side equated with this side and you want to isolate the probability of this intersection, you see that the probability of A intersect B is the probability of B given A times the probability of A. So right here, I have two different ways to write down the probability of the intersection event of A intersected with B. Again, I'm taking a conditional probability definition and using it to get an intersection probability expression for which there are many. And we can draw some Venn diagrams and get many more, but it is going to be super central to everything we do in here to look at the probability of an intersection as a conditional probability times what is known as a marginal probability. It's a probability for one of the events alone. So let's turn to random variables. Suppose I have discrete random variables, capital X, capital Y, capital Z. We can talk about the probability that capital X equals a number like 1 or 1.2. Even if it's discrete, that doesn't mean it's integer valued. So in general, I want to talk about the probability that capital X equals some lowercase x, where this is a stand-in for a fixed number. So capital X is a random variable, lowercase x is just standing in for a fixed number. And this thing is known as a probability mass function, or a PMF. It's usually denoted by an f of little x, or if necessary to, because you might use a capital X here and a little y. And so what is the random variable? The probability mass function is attached to the random variable. So you might use a subscript and put the random variable, the capital X, as a subscript on the f, and then the argument, the thing you are plugging in to try to find the probability for. So you heard my little speech at the beginning. That should not be new to you. I now want to review joint probabilities. So if we want to talk about the probability that capital X equals some fixed little x, and at the same time, capital Y equals some fixed little y, the first thing I want to point out is that and in a probability statement is written as a comma. So we're not going to write this word and out. It's like an intersection. It's an intersection of the event that the random variable capital X equals little x and the event that the random variable capital Y equals little y. And in fact, that's going to help us go forward here and define conditional probabilities for random variables, because we're really just talking about events. And we've already done all this. We've already talked about how to get the probability, the conditional probability that A occurs given that B occurs. But I'm getting ahead of myself. A comma in probability means and. As an example, suppose that for discrete random variables, often probabilities are tabulated, not always. But suppose you have random variables, capital X and capital Y, that take on, let's say capital X can take on the values 2, 3, and 7, and Y can possibly take on the values -5 and 11. And suppose they take on those respective values with these probabilities. This is a table filled with probabilities. They are joint probabilities. In fact, let's look at a specific example. What is the probability that X equals 3 and Y? In fact, let's look at a specific example. What is the probability that capital X equals 3 and capital Y equals -5? You're going to go to the 3 here and the -5 here and look at the probability right here. This is 0.2. These are these probabilities in the entire table, so all 6 numbers have to add up to 1. And I hope they do. Yeah, I think I did it. So this is just an example of what these numbers represent. They are joint probabilities for different values for the random variable X and the random variable Y. Now, suppose you want the probability that the random variable capital X is, say, equal to 3. This is a table of joint probabilities. And if you just want to isolate X alone and look at where it's equal to 3, you're looking at these two values right here. In fact, the probability that the random variable capital X is equal to 3 is the probability that X equals 3 and Y equals -5, or we add a disjoint event probability. Think Venn diagrams. If things are disjoint, then to compute the area of this or this happening, that's a union, you would get the probability of one plus the probability of the other. There's nothing to subtract out from the center. So by disjointness of the events, the probability that X equals 3 is the probability X is 3 and Y equals -5, or X is 3 and Y equals 11. Both of these sort of joint events cannot happen at the same time. If you can get X equals 3 and Y equals -5, if that happens, then you definitely did not get X equals 3 and Y equals 11, if that makes sense. So these probabilities are 0.2 and 0.1, and you add them and you get 0.3. So I went from a table of joint probabilities to come up with a probability for X alone. This question was, what is the probability that X equals 3? And to do it, we added up a couple of numbers. And if you continue around this table and total all the rows and columns, what you see are those isolated probabilities for X and Y alone. And these are known as marginal probabilities because they're in the margins of this table. That's sort of the motivation for the original use of the word marginal probability. If you were trying to get a probability for X alone or Y alone, and you start with a joint probability for both of them, you can find those individual alone probabilities in the margins when you tally things up. So once again, this probability that capital X equals 3 is known as a marginal probability in this context. Now, note that if you go across these bottom numbers here, this represents the probability that X equals 2, the probability that X equals 3, and the probability that X equals 7. These will sum to 1 as they should. So when you add up all 6 numbers in the table, you get 1. But when you find this list of marginal probabilities down here or here, those should add up to 1 as well. More generally, the sum over all little x of the probability that capital X equals little x is 1. I could have written this as a sum as x goes from -infinity to infinity and noted that a whole lot of these probabilities are 0. Like, what is the probability that our random variable x for this example is equal to 19? It doesn't happen. So it's fine to put all values in here, but I still did not write x going from -infinity to infinity because that makes it look like x can only take on integer values. So that's why I write it like this. This is a sum over all little x in the whole world, all real x if you want, but I'm just going to write it like this and not worry about being too specific when summing over x. But no matter how you write it, these marginal probabilities, probability that x equals little x when you sum over all little x should be 1. Note that we just saw that you can get the probability that capital Y equals some little y by taking the joint probability that x equals little x and y equals little y and summing out all of the x values. So I'm going to write that like this. And with that, we are ready to define conditional probabilities for discrete random variables. We're going to talk about the probability that capital X equals some little x, given that capital Y equals some little y. This is an event. This is an event A, where A is defined to be the event that X was observed to be little x. And this is the event B, where B is defined to be the event where the random variable capital Y is observed to be little y. So you know how to compute this. You would get the probability of A intersect B over the probability of B, but in terms of the random variables and never dragging those A's and B's in, this is the probability that capital X equals little x, comma, and intersection, capital Y equals little y over the probability, the marginal probability that capital Y equals little y. So that's how you define this conditional probability. And note that this is still just a probability in what I call conditional land. So all the usual rules of probability still apply. For example, once you've observed that your random variable capital Y equals little y, if you write down these probabilities for all little x's and maybe sum them over little x's, you should get 1. I'm not going to do this, but as a point of notation that could clarify what I'm trying to say, this is exactly like saying the sum over all little x's of p sub little y of the probability that x equals little x. So the sub y is there to remind you that this is not straight up regular probability like drawing from the deck of 52 cards. Something has changed and we have conditioned on a piece of information. But when I write it this way, this is just another kind of probability function, and maybe it's easier for you to see at this point that the standard rules of probability will still apply. I am going to stick with the full notation like this, though. So let's talk about unraveling in the random variable setting. The conditional probability that capital X equals little x, given that capital Y equals little y, is the probability that x equals little x and y equals little y over the probability that y equals little y. And if I want to isolate this intersection probability up here, we can say that the probability that capital X equals little x and capital Y equals little y, we can write this as the probability that x equals little x given y equals little y times the probability that y equals little y. So we can write a joint probability as a conditional probability times a marginal probability. And we also can do this the other way around, just like we did before when we talked about events A and B. So I can write the joint probability for capital X and capital Y as a conditional probability in the reverse direction times the other marginal probability. This is, again, what I call unraveling the definition of conditional probability. Here is yet another case where I have two formulas for the same thing. I can write this joint probability this way or this way. Which one do you use? It depends on what you're trying to do and what pieces of information you have. It is a blessing, not a curse. It should not be frightening that there are 40,000 ways to write everything in what we're doing in this course. It is a good thing. It allows you, well, I should say that you should remain flexible at all times and realize just how many tools you have around you, and they are not to be memorized because you will go insane. So just stay flexible, keep breathing, and work with what you know, and you will get there. And you will get there every time, I promise. Okay, so check this out. Suppose I have random variables capital X and capital Y, and suppose I want to know the probability that capital X is equal to little x. We do know that if for some reason we only have the joint probabilities, we can get this by summing over all little y, the joint probability that capital X equals little x and capital Y equals little y. And if this is what you have to work with, great. This is a way to find this marginal probability. But you might be given different information in a problem. And note that we can use our unraveling trick here. This is also the sum over all little y of the probability that capital X equals little x, given that capital Y equals little y, times the probability that capital Y equals little y. Now, if you go directly from here to here without thinking about this step, you are doing what we call you are finding a probability for x by conditioning on the value of another random variable y. The initial problem did not involve y, but sometimes it helps to bring that in. As an example, not involving random variables, in your basic probability course, you probably had boxes or urns or drawers with socks or balls, colored balls, and maybe you have a certain number of different colors balls in each of your urns, and you want to randomly select an urn and say, what is the probability you get a green ball? It's definitely an easier question to answer once you know maybe which urn you're in. So even though you only care about the probability of getting a green ball, you end up conditioning on, well, if I fell in this urn, the probability would be this. And if I fell in this urn, and so conditioning on things like this generally reduces the problem to smaller problems that you might be able to tackle. It's a good thing. Okay, all of that may have been review for you, and as well as what I'm about to do now, but I am going to step it up a notch and things are going to get hairier. So hang on. Suppose now that I have random variables, capital X, capital Y, and I want to suppose my goal is to find a conditional probability that capital X equals little x, given capital Y equals little y. And for some reason, it is convenient, think of the balls and the urns and whatever. It is convenient to compute this by conditioning on a third random variable that I'm going to call capital Z. Before doing this, I just want to write down some notation. Note that the probability that x equals x, given y equals y, given z equals z is what I would call ooky, and that is a technical term. This is just weird. Don't write it. It doesn't make any sense. Once you are given both pieces of information, that y equals y and z equals z, that's what you've got. You've got that information. So really, you're just computing the probability that capital X equals x, given the full information that y equals y and z equals z. So never have two conditional lines like this. It's very bad form. So let's go back to the task at hand. I want a way to write down this conditional probability by conditioning on z. Before I do that, I want to recall without conditions that the probability that capital X equals little x, we could write this as the sum over all little z of the probability that capital X equals little x, given capital Z equals little z, times the marginal probability that capital Z equals little z. This is not the problem I wanted to solve, but I do want us to mimic this formula in conditional land where capital Y has been fixed to be lowercase y. I'm basically going to write this formula again, but I'm going to stay in conditional land where capital Y equals lowercase y. So I'm going to replace this probability that x equals x with the probability x equals x given that y equals y. And I'm going to replace this conditional probability that x equals x given z equals z with the probability that x equals x given z equals z and also given that y equals y. And I wrote them alphabetically because I thought it looked nicer. And finally, this marginal probability that capital Z equals z, I'm going to write this as the probability that capital Z equals z while staying in this conditional land where capital Y equals y. So every term here has y equals y after the conditional line for sure, and some other things pop in as we condition on z. But look at these two formulas and realize how similar they are. We just are rewriting this, a formula we already know to be true, in the universe where y equals y. That's all that's happening. Let's prove that this formula actually does what it's supposed to do. It's one thing to say I've mimicked this other formula, but let's make sure that this holds. So I am going to, so here's what I want to prove, and I'm going to start with the right side. So let's just write down that right-hand side here. There are many ways to prove this, so you might not take the steps I'm going to take, and that's fine, assuming you took correct steps. But over here, this conditional probability for x equals x, given the two things, I can write this as the intersection that x equals x and the other stuff. So that's going to be a three-way intersection that x equals x and y equals y and z equals z. And then I'm going to divide by the probability of the stuff after the conditional line. For this conditional probability over here, I'm going to write this as the probability of the intersection of the two things, and I just rewrote them alphabetically because I thought it looked nice, over the marginal probability that y equals y. And once we do this, we see that we have some cancellation, and I have to deal with this sum over here. We started with this right-hand side. I'm trying to show this left-hand side. There's certainly no sum. I think we're going to have to sum over all of these z's. So check this out. I can pull out this denominator 1 over the probability that capital Y equals little y because there's no z here. And now I am summing a joint probability for 3 random variables over all the values of little z. And that's going to marginalize out that random variable capital Z leaving us with just the joint probability that capital X equals little x and capital Y equals little y. And this 1 over the probability that y equals little y is still sitting there. This is the probability that capital X equals little x and capital Y equals little y. And that's exactly what we wanted to show. So we have proven the claim. Again, I want to remind you that it is important in this course to stay super flexible. I'm going to have another proof later today. We're going to fit it in, I think. And there are so many different directions I could have taken. And I can't even tell you necessarily that I have an optimal direction, but you got to stay flexible. Think about what you're doing, draw pictures, but don't get hung up in memorizing formulas because it's just not going to work. It's just not going to work. So stay flexible, keep breathing at all times. Okay, so that is the end for now of my review of conditional probability, especially for random variables. We don't care so much about the A given B, but the X equals X given Y equals Y sort of thing. Let's get back to defining a Markov process. I have one more thing before that, and to talk about a stochastic process, I just want to make sure that I say one thing. So the random variables in a stochastic process, so this is my collection, and I have random variables in here, x0, x1, x2, etc. They should all be taking values from a common so-called state space. In here, you could call this omega, like we did for our set of all possible outcomes of an experiment. For a stochastic process, it's usually not an omega, but there are many symbols. I'm going to use a capital S to denote the state space for this stochastic process. And you might use, some people use a big curly looking X if they're talking about a sequence of XNs. There are so many things you can use. I don't care what you use in here as long as, you label things and I can tell what you're doing. But note that the state space has to be common to all of the random variables in a stochastic process. So while it may be the case that whatever we are measuring here through time, it may be the case that x0 can only take on values in the set 1, 2, 3, and x1 can only take on values in the set 4, 5, 6, etc. The state space would include all of those values. It's just that the probability that x0 equals 4, 5, or 6 would be 0, but it's still considered a potential value for x0. So the state space is the set of values that the random variables can draw from, and it's common to all of them, even if they can't all actually turn out to be all of those values. Now you've waited long enough. Let's define a Markov process or Markov chain. I'm going to change my language here in a moment and tell you why. So I'm going to let capital S be a discrete state space. And random variables are always assumed to be numeric. They are actually functions from a space, a set of outcomes of something involving probability into real numbers. For example, if you flip a coin, a fair or unfair coin 3 times, the possible outcomes there are not numeric. They're things like heads, 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 tails, etc. But if you let a random variable x be the number of heads in those 3 flips, then you get values like 3 and 2 and 1 and 0. So you take values from a kind of abstract space often, and you produce numbers, which I can say are in the real numbers, even if we're actually further restricted to integers or something like that. That's okay. Integers are real numbers. But the state space for our Markov chain is a set of possible values that random variables can take. So this has to be numeric. And so here's my definition. I've held it off way too long. Let S be a discrete state space, because we are talking discrete in today's video and for the first third of this semester. The discrete time stochastic process, the collection capital X0, capital X1, capital X2, etc., is said to be a Markov process or Markov chain. I'll come back to that. If. So I've got this long, funky conditional probability statement here. If the probability that capital X sub n plus 1 equals j, given x sub n equals I, and x sub n minus 1 equals I sub n minus 1 down through capital X sub 0 equals I is 0, if this equals just the conditional probability that capital Xn plus 1 equals j, given that capital Xn equals I. Whew. Okay, so I enumerated potential values from the state space. I call them little I0, little I1, little I2. I stopped here at little I n minus 1. I could have called this I, little I n, and I could have called this j, little I n plus 1. But for reasons that are not yet apparent, I wanted to really sort of highlight those two values as their own special things. So yeah, I'm talking about a process that basically you observe a history you are given, you have observed that at time 0, you were in some particular numerical state I0. At time 1, you were in some particular given numerical state I1, etc. And then where you go at time n plus 1, given the entire history of the process, the probability of moving to j does not depend on where you were before time n. This statement has to hold for all n equals 0, 1, 2 on up, and for all I0, I1 up through in minus 1 and I and j from the state space, and it has to hold wherever these conditional probabilities are defined. Ignore that line for a moment. I'll come back to that and make sense of that later. But this is right here. This equality is known as the Markov property. It says that where your chain is going, given the entire past history, it's not important. It just depends on where you currently are. So you can think of time n as where you currently are, and then the probability you go to state j at the next time step at time step n plus 1. To compute that probability, I don't need to know where I was before the current time n. This is the Markov property. So before I move on from this slide, I said chain. You'll often hear people talk about Markov chains, and I'm going to start saying that here. The term chain is generally what is the word? The term chain is generally reserved for a discrete time process. So a Markov process, just to call it a process, is more general, and you'll never be wrong calling it a Markov process. I wouldn't use Markov chain when I get to continuous time, but if you do, it's really not the end of the world. So Markov chain, Markov process, essentially the same thing, but the word chain is reserved for a discrete time setting. Think of it, it's a chain of values that you're building up in time with various probabilities. Let's look at an example of a Markov chain. So suppose I have 2 green balls and 4 white balls, and I put them into 2 urns or boxes or drawers labeled, I'm going to say urns, so labeled urn 1 and urn 2. And suppose I put these balls in such a way that at every point in time, because we're going to start a process, we're going to start moving things, but at every point in time, each urn contains exactly 3 balls. So I've got my 6 total balls distributed into 2 urns, 3 and 3. And at each time step, I'm going to randomly select a ball from one urn and randomly select a ball from the other and switch them. I'm going to let xn be the number of green balls in urn 1 at the nth time step. I claim that when you collect all these random variables, x0, x1, x2, etc., that this is a Markov chain. So what is the state space? The possible number of green balls in urn 1 at time n, there could be no green balls. It could be white balls only. There could be 1 or there could be 2. So that is the state space here. And let's look at I'm going to look at a very specific probability just to make a point. What is the probability that x7 is 1 given a bunch of stuff? So at the 7th iteration, I'm going to start this process somehow. And at the 7th iteration, what's the probability I have exactly 1 green ball in urn 1? Given that this is what I saw. Given that at time 6, I had 1 green ball in urn 1. And at time 5, I had 2 green balls in urn 1. And at time 4, I had 1, and so on. So you can see I actually started this process at time 0 with 2 green balls in urn 1. What is this probability? How would you compute it? You would look at where you currently are at time 6, where I have 1 green ball in urn 1, depicted like this. Now, what is the probability? I still have only 1 green ball at the next time step. Do you really care what happened to get you up to time step 6? No, because you're going into both urns and randomly selecting a ball. And so how do you still have 1 green ball? That will happen if you grab a green and you switch them so nothing has changed, or you grab a white and you switch them so nothing has changed. That's the only way you can go from having one green ball in one time step to having one green ball in the next time step. And it's pretty easy, I think, to believe that none of this depends on what happened before to compute this probability. So given the setup of this problem, I don't need to know the history. This is just going to be the probability that given at time 6, I have one green ball and earn 1. At time 7, the probability I have one green ball, we're just going to look at those two moves. This is a Markov chain. And that is sort of my conversational proof of that. I don't need to know this stuff in order to compute this probability, and knowing this stuff is not going to change anything about this probability. So what is the probability that at time 7 we have one green ball and earn 1, given that at time 6 we had one green ball and earn 1? Again, you should think about this, this time step over here as currently. Currently, we have one green ball and earn 1, and we're going to make a move. And in the next step, what is the probability? We still have one green ball and earn 1. As we just said, this is the probability you draw a green from earn 1 and a green from earn 2, or the disjoint event probability that we get to add on, the probability you draw a white ball from earn 1 and a white ball from earn 2 and switch those. And now at time 7, you'll still have only one green ball in earn 1. And what is the probability? You draw a green and a green when you have this setup, because this is representing what's happening at time 6. This is going to be the probability you draw a green out of here is 1/3, and the independent draw over here, that probability is 1/3. Whereas the probability you draw a white over here is 2/3, and you're drawing independently from this urn, because I don't know, did I say that? I think you would have to assume that, because otherwise I would be giving you more information. Like, given that you drew a green ball from urn 1, now you go into urn 2 and draw 2 and switch them. I mean, where would the dependence be? So sometimes I don't explicitly write independent draws where I should have, but I think this should be clear from this problem, because otherwise I'd have to give you more information. Anyway, let's finish this up. Draw a green from here, that happens with probability 1/3. Draw a green from here, that happens with probability 1/3. We get to multiply them to get this probability. And then drawing a white from here, that happens with probability 2/3, and a white from here with probability 2/3. We get to multiply them to get this probability. In the end, we get 5/9. And this is easy. I hate to use the word easy to see, because maybe you don't see it, and everyone, easy is in the eye of the beholder. I say all the time. But the past history and how the ball's gotten to this position does not matter. And that is why this is a Markov chain. Now, we only looked at one small case. I wouldn't call this maybe a rigorous proof of why it's a Markov chain, but hopefully it makes sense to you that this is a Markov chain or a Markov process, the evolving 0s and 1s and 2s in the green ball from earn 1 count. Okay, so let's, to finish off for today, go back and talk about that final line in the definition of a Markov process or Markov chain. It was kind of a throwaway at the time. It said, whenever these conditional probabilities are defined. So we just argued here that the probability that x7 equals 1, given this entire past history, is by the Markov property. So when I write an MP over an equal sign like this, I'm using the Markov property. We just showed or argued that this is equal to the probability that x7 equals 1, given x6 equals 1. But what if I change out this number here for, say, 2? Something has gone wrong with the past history of the chain, because I started with 2 green balls in earn 1, and then I went to 1, which means I took one out and replaced it with a white ball, and then I went down to 0, and then I stayed at 0, and then I jumped up to 2. And that can't happen. At most, if you have 0 green balls, when you switch a ball, at most you can get, so you have to take out a white ball. And you might grab another white ball and switch them and nothing happens. Or you might grab a green ball from the other end and switch them, and now you have 1 green ball. There's no way to go from 0 green balls in earn 1 to 2 in one move. So this does not make sense. And as a conditional probability, this stuff after the conditional line is really a probability that's going to appear in a denominator. And that probability is going to be 0. The probability of all this stuff occurring is 0. So in the denominator, 0 is bad. This is undefined. But this probability over here is still well-defined and is still 5/9. So is this no longer a Markov chain or Markov process? It's okay because of that line at the end of the definition. As long as things like this hold wherever both probabilities are defined, it's all good. If it's not defined, it wouldn't have happened. You're not going to observe that. So don't worry about the Markov property. If one of them is undefined and the other isn't, then you shouldn't even be thinking about the Markov property. Something is fundamentally wrong with your process. Okay, so it looks like we're out of time for today. That 5/9 we just computed was the probability of going from one green ball in one time step to one green ball in the next time step. And I don't think the actual time of the time steps mattered, do you? If we have at time 99, after 99 trials of this experiment, one green ball and earn one, what is the probability we'll have one green ball at time 100? The same thing is still going to apply, and we're still the same procedure for solving that. We're still going to get 5/9. So next up, we're going to talk about a possible so-called time homogeneity property for our Markov chain. And we're going to get down to business of organizing all of these one-step transition probabilities, going from one green ball to 0 green balls, or one green ball to 2 green balls in any one time step, be it between time steps 6 and 7 or 99 and 100. We're going to organize all the transition probabilities into a matrix and do really fun things with that matrix. So I hope to see you in the next one.